everyone. Welcome to our talk, Scaling Services with Distributed In-Memory Cache. I'm Divya.
And I'm Chirag.
And we are, as Eric told, we are product engineers at Gojek. This talk is about how we attempted to remove single point of failures from one of our web service and scale it using distributed in-memory cache. So many of you might not know what Gojek is. Gojek is Indonesia's largest ride-hailing startup. We primarily work in logistics and payments. It was founded in 2010 and is one of the unicorn in Indonesia. We operate across 40 cities and have approximately 900,000 drivers, which includes both bike drivers and car drivers. We serve 100 million monthly orders, impacting around 261 million people across Indonesia. So this is what our customer app looks like. It got launched in 2015, and the growth has been exponential since then. We have 18 plus product, which serves 3 million orders a day. The scale at which we operate, our users expect us a smooth user experience. It has to be slick, which means that our systems should have low response time, and they should be highly available. To achieve this particular goal, we embrace a microservice architecture in our systems so that our teams can grow and they can scale independently. So
recently, we had an incident in Gojek wherein a few 100,000 users of our system got logged out. Think about you using Uber and you being logged out and not being able to log in back. That's exactly what the situation was. On social media, we were seeing posts bombarded by all the users that, hey, I'm logged out and I'm not able to log in back. And same was the situation on the customer care side. What happened next is our support team immediately investigated the issue. And they identified that all the application instances of the authentication service were down. Think about authentication service instances being down. It's like you won't be able to use the application at all if the authentication service is down. From the architecture standpoint, we had a few application instances behind a load balancer. Each one of those was talking to a central cache for accessing the data quickly, and we used to revert back to the database in case the data wasn't present in the cache. Well, it was a fairly straightforward system, but even then it went down. What could have been the cause of the problem? When our engineers further investigated the cause of the problem, they realized that it was the Redis cache which went down, which led to a cascading effect across the infrastructure. What they basically figured out is that by looking at the logs of the application and the application metrics, they saw that there was a huge spike in the throughput of the application, which led to a massive load increase on the central cache, following which the cache ceased to respond and it just went down. As a result, the application instances started panicking out, and the entire service was unavailable for a certain period of time. Well, at Gojek, we strongly believe in a philosophy of testing our systems thoroughly so as to identify and eliminate all possible bad parts or scenarios upfront without even launching the app in production. We just do that step before launching. However, mistakes do happen since all of us are humans. So we at least tend to, even if the mistakes happen, it's our responsibility to figure out what caused the problem so that we can resolve it in the shortest period of time. In our particular use case, the question was this a testing error? Was there a logical mistake, or what exactly was it? Well, more importantly, it was a single point of failure problem. Our cache went down, which led to a cascading effect across the infrastructure. We learned a lot from this incident, and it basically taught us that, hey, we need to now visit all the other web services which are there in our infrastructure and investigate if they also share the same problem. And our responsibility now was to come up with different architectures which could, if not completely remove, but at least reduce these problems from happening in the future. So as a team, we basically decided that, hey, now we're going to go back and investigate if there are other services which share the same problem. So the only goal that we had in mind was we will be looking at the services which have a central database or a central cache, and we'll be investigating that just in case it goes down, would the service still continue to operate, or would it just go down? So that is the idea which we had in mind, and that's exactly what we did. So in this talk, we'll be going over one such use case of a service and see how we manage to reduce, if not completely remove, single point of failure from the system.
So after system auditing, this was the particular service which we picked up. So we worked on this web service which which grew in terms of scalability requirements in a relatively short period of time. So by scalability, I mean that a service or a microservice which can not only handle large number of requests, but which can handle them efficiently and effectively. This web service is called Surge. So Surge was responsible for increase in price whenever there is a high demand. For example, if you are trying to take a ride from one place to another place, and if there is a high demand going on in that particular area as compared to supply, you might be charged some extra price for the same ride. And this was done to make sure that people who need a ride get one reliably. So Surge basically did two things for us. One thing is it calculated a surge multiplier, which was being multiplied with the price in order to get the full price. Another thing which this web service did is it exposed an HTTP API called heat maps, which is basically this. Heat maps was there to direct the driver wherever there is a high demand going on. So as you can see, you might see some red, orange, and yellow blocks where red implies that in this particular area there is a high surge, so you can go there and balance the supply. So there were few major challenges which this particular API gave to us. Those were high throughput and high availability. Heat maps were there on the home screen of the driver. So driver were continuously requesting the updated heat maps so that they can get the surge information, which means that incredibly large amount of concurrent requests at any point of time. Another thing is that it needed to be highly available, on failing which drivers felt that they are not being incentivized enough in case of high demand. So the question was, how do we design such an architecture which can handle this much throughput and can handle it effectively?
The first implementation of our architecture was a fairly straightforward one. Well, we had a Kafka pipeline from which we consumed the necessary data. This data primarily included the metrics of demand and supply, using which we could compute something called as a surge factor, which is nothing but a number which needs to be multiplied by the price, which requires the customer to pay more price in case there is a higher demand, and basically pays a driver an incentive for completing that booking. Supply in this particular case refers to the number of drivers in a particular given area at a time, and demand in this case refers to the total number of bookings in a given area at a particular time. Once we consume these particular data points, the application instances now were responsible to parse this data appropriately and persist it in a database. On the other hand, we used to have worker instances which were picking this particular data on a per minute basis and computing a metric called surge, which they used to persist in the database back. Next, we had something called as heat map, which was nothing but a couple of API instances which consumed the data of Surge from the database and exposed an HTTP API called heat maps, which helped the drivers go to the right locations wherever the high demand was. So this was how the earlier architecture of our system which used to look like. There were a few failure modes associated with this architecture. As soon as we launched this particular HTTP API to more and more drivers, we eventually saw a huge spike in latencies when we released this API even further, as well as a massive spike in load time and again. Due to a latency spike and a load spike, there were spikes in number of connections established as well, because the database pool is limited, and you see database pool being congested given that there is a huge spike in latency. Following which, we quickly realized that the database was becoming a central point of failure for us. In order to solve this problem immediately, what we could have done is to vertically scale the database, because the problem was mostly around latencies and the problem was mostly around load. If we would have vertically scaled the database, it would have worked for the temporary bean. But we instead went for a caching approach, wherein from the application instances, the one in the yellow, we tried to prefetch the data for search and persist it in the local memory in the cache. Now, all the heat map instances started serving data from the cache, but they were still reliant on the data to be fetched from the database. What we did, this is the thought that we had in mind, and this is what we implemented. But we knew that we could have possibly done a better approach, maybe removed the dependency on the database completely from the picture.
Yeah, so we could have done better. We decided to optimize our systems. What we did is we decided to take a step back and rethink about our architecture if there are any improvement possible in that. So we took these two use cases of ours. One is search and another is heat maps. And we started analyzing them, that how they can be differentiated. So in terms of consistency, if you say that search had a really high consistency requirements, the reason is that search is directly being used in price calculation. And when you deal with money, you can't really afford to have data inconsistency. As I previously told that we do 3 million bookings a day, which means that a minute mistake in search can lead to significant monetary loss, which we did not want. On the other hand, if you see heat maps, it's just a visualization tool for search. It was there for the drivers to direct them in high demand areas. The data points were ephemeral, they were changing every minute because drivers were changing their location every minute. So it required high throughput, it required high availability, but consistency was something which could be compromised in case of heat maps. So that was the major difference. When I say that consistency could have been compromised, which means that in the entire map, one cell might not show the updated data of the search, but that will still work out. Apart from that, this was our previous architecture. And where we were using cache, which was refilling itself by prefetching from the database, there were two major problems with this approach. First, if you increase the number of nodes in heat maps, it will increase the load on the database as well. Another thing, search was a very critical component. Search was using the same database to store the search multipliers. And heat maps was using the same database as well. So we wanted them to separate out so that a relatively less critical component heat map does not affect the relatively higher critical component search. So these were the major difference. Apart from that, what we also get to know that search and heat maps, both of them have very different scalability requirement. If you see the throughput graph, this throughput for the search API is approximately 10,000 to 12,000 requests per minute. On the other hand, heat maps API has almost 10 times of it. So now what we decided that the question in front of us which came is that how do you design an architecture which can manage these two components which have very different scalability and criticality requirements, while considering the fact that they both use the same data source to operate?
Well, now it was more of an experimentation. So what we did was we went over to the books and came across this book, amazing book by Michael Nygaard called Release It. And in this particular book, there is a concept called shared nothing architecture. The shared nothing architecture basically signifies that all the application nodes in your cluster would operate independently without actually relying on communication or calls to any other node in the entire ecosystem. The advantage with this approach is that given that you add more nodes to the system, they could just scale up more linearly without relying on anyone else. So let's take a more practical example. Let's take the example on the left. The example on the left relies on a central data source, and just in case the data source goes slow, the latencies would increase if you expose an API over there. However, in a shared nothing architecture, the latencies is a complete function of how slow your application is behaving since it does not rely on anything else. Another thing that it mentions is that the uptime of your system is a function of the uptime of your dependencies. So in the example on the left, if the database goes down, for instance, your system would just stop working. However, with the example on the right, if there is no database, so there's practically nothing which could go down apart from your application, which can be logically tested. So we realized that a shared nothing architecture was a completely suitable use case when it comes to an implementation of heat maps. So on a very, very broad perspective, what we wanted is such an architecture wherein heat maps, which was comparatively less critical, in case it goes down, we're not supposed to take surge down along with. So that was the idea which was constantly hitting our minds. So let's see how we further went to imagine a new architecture wherein we isolated the database only for the surge calculation part. And in order to scale the heat maps and surge independently, we wanted to replicate somehow the data from the worker instances, which were producing the surge multipliers, over to the heat map instances, which were using those multipliers to be able to expose HTTP APIs for heat maps. So speaking in a very, very broad term, let's say you have n number of nodes in your cluster, all of which are producing some data of some kind. And that data point needs to be exchanged or synced across all the other nodes in the cluster. What you needed basically is a way to identify who those nodes are, whom you need to exchange the data points with. And you need some way to be able to replicate those data points across to other set of nodes in the cluster. In short, we basically needed a distributed cache. From a bird's eye view, the feature of the distributed cache that we needed were that it needed to be in memory so that the data retrieval could be super fast. It needed to be distributed so that the downtimes would be none. Needed to be replicated so that we could remove the dependency on any centralized data source, in this case, a database, for instance. And it needed to be horizontally scalable, wherein addition of new nodes into the cluster could linearly scale the number, the application as a whole.
Okay, so we needed a cache. So in order to solve the problem of transferring the transient data between nodes, we built Prattle. It is a distributed replicated cache, and underneath it uses concurrent maps. It primarily solves two problems for us. First, it persists the information of all the nodes into the cluster and replicate that particular information using gossip protocol. And whenever it exposes a set, it exposes a set API, which internally replicates the data across the cluster using best effort protocol. So Prattle does three things for us. First, it manages membership, which is basically answer to the question that who all are the nodes in my cluster. Second thing is replication, which means that once I set a particular data in a node, how does this data gets replicated in the entire cluster? And the third thing is cache, which is basically persisting the information in every node. So the first problem which we needed to solve for this is membership. So in order for Prattle to replicate the data, it first need to know that what are the nodes, other nodes in the cluster. Now, how do we figure that out? A simple approach which we took is heartbeating. There can be multiple ways to identify who all are the nodes, but we took the heartbeating approach. So in heartbeating, what you do, every node will send heartbeats, which are basically align messages to all the other nodes at some particular time period. And all the other nodes in the cluster, they will keep the list of the nodes who are sending the alive signals. So for example, one is sending alive signals to 2, 3, 4, 5, 6, and all of them will keep one as the cluster member. Now, for example, if you have 6 nodes, you will be transmitting approximately 36 messages across the cluster, which is not a problem. It doesn't, it works fine. But what if you have like 9 nodes, you will be transmitting 81 messages. But if you have 1,000 nodes, you will be transmitting 1,000,000 messages across the cluster. Which now, so basically what I mean to say is that number of messages increase quadratically with the number of nodes. But why sending more messages is a problem? Sending more messages becomes a problem in case of membership. It creates another kind of problem which is called false positives. So now what is false positive? Let's say, as I showed in the previous image, node 1 was trying to send alive signals to all the other nodes, but due to some reason, if that particular message gets dropped, then for node 4, node 1 will be dead, and it will update its member as 2, 3, 4, 5, 6. When more messages will get dropped, it will create more inconsistency across the cluster. So in this particular example, For 6, the view of the cluster is 1, 2, 4, 5, 6, while for 4, the view of the cluster is 2, 3, 4, 5, 6. Which means that when you have thousands of nodes and millions of messages going across the network, and more messages are getting dropped, different nodes might have different view of the cluster at any given point of time. So more messages lead to more message drop lead to more false positive, which leads to more inconsistency across the cluster. So now how do we figure out a way so that we can get all the members of the cluster reliably?
Well, all we needed to do was that given a node, figure out all the peer nodes in the system for whom we need to replicate the data to. In the previous implementation, what we explored is that it was called heartbeating. The two problem points associated with that were it incurred a massive network congestion, and it led to a lot of false positives. An industry standard approach to do that is using a gossip protocol. Think of a gossip protocol as a simple implementation wherein if there is a person who is infected with a certain disease and he moves into a group wherein the group doesn't have that disease, there is a high possibility that the group will have that disease given that the person moves in. That's exactly how gossip works. So in this particular use case, looking at the picture, one tries to exchange a certain state with a subset of its peers. And all those subset of its peers tries to exchange that state with a subset of their own peers until a state wherein the entire cluster has the same view of the world. This particular implementation is known as SWIM, which is basically Scalable, Weakly Consistent, Infection-Style Membership Protocol. Using this protocol, we were successfully able to implement or at least figure out who the members of a particular node are, or who the peer nodes are for a particular node in the cluster. Going into further depth, let's look at code and let's look at how a particular node figures out who its peer nodes are. For instance, we have two nodes to start with, node N1 and node N2. What node N1 needs to do is it needs to identify whether node N2 is alive or not. What node N1 does in this case is that it establishes a ping request and creates an acknowledgement channel to receive an acknowledgement back from node N2. Next, it tries to ping node N2 with that ping request and waits for an acknowledgement from it. If it gets the acknowledgement successfully back from node N2, it basically marks node N2 as healthy in its list of members, which basically means that now N1 knows successfully that node N2 is alive. However, if it fails to receive an acknowledgement back from node N2, what it does instead is that it tries to probe node N2 via some other nodes. One reason why this situation could be possible is that, let's say there could be some network congestion between node N1 and N2, which is why there is a possibility that some other node in the system might be able to communicate with node N2. What node N1 does now is that it tries to probe node N2 using some other nodes in the cluster. So what it does instead is that it figures out k random members in the entire cluster. In this particular use case, it figures out node N3. What it does next, it basically creates an acknowledgement channel to receive a message back from node N3. The next thing that it does is that it tries to send a ping request to the node N3 and waits for an acknowledgement, like so. If node N2 is successfully able to acknowledge its alive status to node N3, node N3 now replies back to node N1 that, hey, node N2 is alive. And if the node N2 is alive, node N1 marks that node N2 in its list of alive peers. However, if that fails, node N1 marks node N2 as not alive and disseminates that particular information using a gossip protocol. Until now, with this implementation that we've shown over here, we were able to successfully at least identify who these peers are for a given node by actually incurring far less network congestion and guaranteeing fail safety, wherein we don't actually remove a node from the system which is actually not dead, which was the sad part or the bad part about the heartbeating approach. Now let's look at how we replicate the data across all the other nodes in the cluster.
Great. So now we know that who all are my peer nodes. We have enough information to replicate the data across the cluster. So let's see how we solve the second problem which we had with Pretel is replication. So this was our initial approach. What we did is we were sending alive messages to all the other nodes and using gossip protocol to transmit the alive information. We piggybacked the information which we want to send across the cluster with the same ping request and used a swim-based replication approach in order to transmit the data. So this was a Pratel implementation for it. You just initialize new Pratel and it takes sibling address so that it can basically join the existing cluster using that particular address. And another thing which Pratel does is it exposes an API which is set via gossip. You give a key value pair to it and it will start transmitting this data across the cluster. Now, we implemented this and we started doing the benchmarkings and these were the results. So is this graph visible out there? Okay. So in this graph, the green graph denotes the total number of messages which we are trying to replicate, and the yellow denotes the total number of messages which actually got replicated. So as you can see, we were trying to replicate approximately 10,000 messages, while the replication rate was not as expected. It was just we are able to replicate only 6,000 messages, while considering the fact that this benchmarking was being done with a cluster which only had 5 nodes. So definitely this approach was not suitable for our heat maps because the throughput which we had on heat maps was like 100,000 requests. So we decided to analyze the problems with this particular approach and why Gossip is not able to scale for us. So there were few problems which we could come up with. For example, when we explained Swim uses, first thing, whenever it sends alive messages, it waits for an acknowledgement. It waits for an acknowledgement to come, and then it does probing, and it does like retries basically via another nodes if go and check if this particular node is alive or not. This particular thing makes Swim slow for fast replication. So we needed a way to figure out that how can we replicate the data fast enough so that it can manage the load of the heat maps API. Let's see how we went about it.
So since the implementation that we had for replication in the version 1 was very slow, we instead went for a UDP-based, a multicast-based replication. The name might seem fancy, but the idea is very simple. You have a node. If there is a change in the state of a particular node, what the node now needs to do is that it needs to now disseminate that information to all the other nodes in the cluster parallelly. Also use UDP in the process because it's non-blocking. That's exactly the idea. It's very simple. The implementation of the library that we are made exposes another API called setViaMulticast, which internally takes in a key value, and it uses UDP multicast-based replication to disseminate that information across all the members in the entire cluster. And we actually got very interesting results with this particular implementation. We were successfully able to replicate approximately 180,000 messages across a set of 15 nodes in our cluster. And that is a metric for these messages per minute. And that was really interesting. The one that you see in yellow in the graph basically signifies the number of messages that we were able to replicate per minute. Another one which is missing from the graph is the one in green, which is the number of messages we were able to produce. The reason why the green part is not visible is because yellow is completely overlapping green, which basically signifies near real-time replication. So until now, we have been able to figure out who the members are whom we need to replicate the data to, and we have figured out how to replicate the data. Taking a step back, what we needed was, given a few set of nodes, all we now need to do is to figure out how to implement the cache in the node. The way we would do that is that we would ship Pratel as a library dependency, which now would be present on every node in the system. All we would need to do is set a particular state on a single node, and that state would be replicated across all the other nodes in the cluster. Taking it back to the actual use case that we had for heat maps, what we could do now is, since the worker instances were actually producing that data, and the heat map instances were consuming it, instead of relying on the database, we could just now produce the data and set it on the worker cache, which would now replicate it to all the instances of the heat map without actually ever relying on the database. So that was the approach that we took to, if not completely remove, but actually reduce single point of failure of the database from a system which had very massive scalability requirements. Thank you. Any questions?
One question regarding one slide, you talk about reduced network communication. Compare one circle one, the other one second. I don't want to get at the part, how do you find the hero approach?
Can you help me identify the slide?
Yeah.
This one? So the idea over here was to signify that the newer approach leads to lower network congestion.
Yes, and how do you achieve that?
The way you achieve, right. So the way you achieve that is using this particular approach, wherein a particular node does not send its alive status to all the other nodes. What it does is it basically only sends it to one node at random. In this particular case, node N1 sends its alive state, tries to identify whether node 2 is alive or not. If the node 2 is alive, it basically marks node 2 as alive in its particular member list and waits for some other time to repeat that process with some other random node. So it's not like it would be pinging all the nodes in the system together, which was the earlier implementation, which was a very brute force implementation. And given that N2 is not alive, which is this particular scenario, it basically uses such an approach of gossip-style information dissemination, which is it communicates to a subset of its nodes that, hey, now node 2 is dead, which is this particular case. And this information is gossiped among other peers eventually, hence making the state synced across the cluster. Does it answer the question? Yes.
Then later on, when you made some improvement, did you just eliminate that the Redis implementation?
Well, the Redis implementation was just a use case that we wanted to describe around how single point of failure problems, how it leads to problems. So the implementation that we had earlier is that we did not have an automatic failover from the slave to the master. So let's say the master went down, someone had to manually come into the infrastructure, promote the slave to the master. That was just a use case that we want to describe around why to have distributed caches. It's not a use case that we actually solved. We instead solved another use case, which is that of heat maps and search.
So are you only using the Postgres for the caching mechanism?
We're not using Postgres for caching. The Postgres is for the actual data persistence. What happens instead is that on every application node, let me go back to that particular slide. So this is the one. On every application node, which is the heat map instances, we are prefetching all the data which is there in Postgres on a regular basis and serving all the data from the cache. However, heat map still relies on Postgres to fetch that data, which means that the more instances you add for heat maps, the more load on the database, and make sure that there is a very high scalability requirement for heat maps. We have like 1 million drivers constantly pinging.
Okay, I may have a few questions. We can take it off.
Sure, definitely. Yeah.
Thank you. One question. So app should talk to cache server, right? Why it's talking to database first?
No. The application is maintaining an in-memory cache internally.
Okay, so
Yeah.
in the app boxes itself you have.
Yes. Yeah.
So I have a question about cache, you need to replicate with your main database, right?
Mm-hmm.
So are you using a pull model or push model?
Well, what we were instead thinking is that this particular approach is a weakly consistent style. It's not very strongly consistent, but it is very highly scalable.
Yeah, I understand you are doing.
So it is more of a push model. It's more of a push model. Where, yeah. So I'll tell you how it is push model. Let's say on one of the cache, you set a particular state. What we do is we use UDP multicast to transfer that state across to all the nodes in the cluster. So it's basically pushing that state to all the members in your entire cluster.
Okay. But this is from cache. You mean the cache broadcast to all the other
Think of cache to be as a library dependency in your application. So let's say you have a Golang application running on one of the nodes. The cache sits along with the application, and whenever you set a state on the cache, that gets replicated to all the other nodes in the entire cluster. So think of each one of these as applications. Each one of these has a cache along with, which is an in-memory cache. It doesn't rely on another node or a Redis instance or nothing like that. It's just maintaining state in memory.
Okay, but the original data has to come from the Postgres.
I'll go back to the implementation once again. In this particular implementation, the worker is producing data. It does two things. It puts the data back into the database and pushes the same data to the worker to the heap map instances. Yeah, that kind of push model. In this particular case, you could completely remove the database for the use case for heat maps, while keep it only for an API which requires very high consistency. For instance, search.
So do all the nodes in the cache today eventually become identical?
There is a possibility that they might not become identical, given that there is a drop in the network packets. But since it's UDP, but there is still a possibility. And as of now, all of our instances are on Google Compute, and we haven't actually seen any significant difference. We have been able to replicate around 99.9% data accurately without any problems yet. But what you say is definitely possible.
Because you're replicating to each node, you have a pretty high memory load on each node? Or is it not that much data?
Well, you would have high memory load given that you're not removing the data eventually from the memory. But what we are doing is we're allowing a facility wherein you can set TTLs as well. So your memory would be swiped off every time it reaches a certain threshold. Or you could implement your own mechanism over it.
Also in this particular use case, we told that the data points were ephemeral, the drivers were changing their positions. So they were anyway getting timed out after a few minutes.
So
that's why we did not face
we were keeping a TTL of about 1 minute for every data point that we had in the memory. So that data point wasn't really necessary thereafter, and it was just getting evacuated from origin.
Any other questions?
I'm just curious, what do you use Kafka in?
Kafka is basically to consume aggregated supply and demand measures. So supply and demand. Supply and demand basically means, hey, in a given area, let's say in this area, how many booking requests have come over a period of time? In a given area, how many drivers are standing over a period of time in that particular area? And we're consuming those metrics into our application, doing the business logic thereafter.
How many cache nodes do you typically say you
Think of all, in the newer implementation, we have been able to scale to 15 or 16 application nodes, each maintaining an inventory cache. So it's nowhere like you would now be having only one Redis instance, which will scale vertically by adding so much memory to it. That's what we did not want, because in the earlier implementation that we showed, our Redis node went down, which led to a cascading effect across the infrastructure. So what we did instead is that 15 or 16 application nodes, all maintaining an in-memory cache. And let's say even if one node goes down, we have so many other nodes which are doing the same.
Is it all in-house or?
This is all in-house. And the application is open source, so feel free to contribute or use it. Yeah.
The cache which we implemented pattern is open source, so this URL.
So before we finish, don't forget to fill out your session evaluation, right?